Hello everyone. So today we will be discussing about HDFS, which is a uh, abbreviation for a Hadoop Distributed File System. So uh, we first be discussing about the need of a distributed file system, why it is required. So the reason being, as we know that with the increasing amount of data that we have been discussing so far, that since the amount of data is keeps on increasing in the order of terabytes and petabytes as well. So to process such data set in a single computer or even a big server was very time consuming, and single system wasn't able to fill in the requirement of hundreds of GBs of data set. So to uh, to process the hundreds of GB of data in a single machine, since it was not possible, then the concept of distributed file system came in, where we can store the data in different chunks in different data nodes. So we'll discuss about what a data node is. Just assume that these are, since the data is not currently available in one machine, and we are not able to put 100 GB of data in one place or 1,000 GB of data in one place. So to to make sure that we are able to store as much data as we want to in the distributed fashion, what we are going to do, we are going to have multiple disks. So this is one disk where we can store the information. This is the disk 2, disk 3, and disk 4. So just assume that instead of storing 100 GB in one machine, we can store 25 GB here, 25 here, 25 here, and 25 here. In such way, if we store the data, then we have the data available in four different locations, which we called as a node. Now, advantage of this is, let's say if I have 25 GB of data available in four different nodes, and if I find a mechanism to process this data parallelly. So if I say that there is a particular application that is running in, let's say it is an app one, and it wants to process the data that is of 100 GB in size. Let's say it is a transaction data, and this transaction data is of 100 GB in size, and I want to process it parallelly so that we can, complete the task in a timely manner. So let's say my SLA is 1 hour, and I want to complete this processing in 1 hour. If I go with a single node architecture, it might take 5-6 hours uh, to complete this job. But if same thing I do in a distributed manner, I will be having four different machines to process the data in parallel. So this 25 GB will be executed in parallel. This will be executed in parallel. This will be, and we would be able to complete those tasks in 1 hour. So it's an analogy like if one person completes the task in one day, and then how many person can complete the task in like in quarter of a day. So something of that sort. So same way, we wanted to use as SDFS, so the distributed file system. So distributed file system is something that we are talking about, and since it is on based on the Hadoop framework, it is called as a Hadoop distributed file system. So what are the advantage of SDFS? It is a distributed file system that is fault tolerant, scalable, and extremely easy to expand. We'll discuss about each terms, like why it is fault tolerant, why it is scalable, and how easy it is to expand it. Then it is a primary distributed storage for Hadoop applications. So MapReduce that we have discussed earlier. Then we have discussed about we have not discussed about HBase, but HBase is a NoSQL database on the top of SDFS. Similarly, we have Hive, which is again on the top of SDFS. These all things comes under the Hadoop framework, and SDFS is the underlying storage layer for all of them. We It is said that Hadoop interface is designed to just work, meaning that you just establish a SDFS framework, and it will be just be working. So for a developer, we don't need to know about the nitty-gritty of how SDFS is created, like how different nodes are joined together. We can just focus on the data and like how to read the data or how to write the data. But we are not like responsible for maintaining this SDFS. But we should know like how SDFS works. So whenever there is a failure, we should be able to debug it, or we should be able to know the root cause, like how it failed. SDFS, main concept of SDFS or a distributed file system was, let's say I have a 3 node machine. Okay, I have a storage over here. So here we have a disk where we have all the data available, and I have this application. So this is a code. Let's say this code is written in Python. Now, if I want to process the data, what if this 100 GB of data is available in each node? So we have 300 GB of data in total. What if we start moving the data towards the code? So this machine won't be able to, handle this much amount of data. So instead of that, in SDFS, what it happens that we move code to the data. So the piece of code that is going to actually process the data, we move it to the machine. So instead of moving from data to code, we move from code to data. So a copy of the code is sent here. This copy of code will process the data that is available in, say, node 1. Another copy will process the data in node 2 and node 3. And finally, when we want to write, it can write in the respective locations. So instead of moving data to code, we with the help of SDFS, we can provide there is a mechanism which actually sends the application closer to data. Okay, so this is one feature about SDFS. Now let us discuss how actually it works, like how SDFS stores the data in a different in a distributed manner. So there are two concepts that we are going to see, or two nomenclature of a distributed framework in SDFS. So there is a concept of a name node, and there is a concept of a data node. Okay, so let's say if we have 3 nodes, so we have DN1, DN2, and DN3. Responsibility of data node is we have to store the data. So data is stored in data node like this. So we will have the data stored in a data node. Let's say I have a file for a transaction data, and this file is of size 500 MB. Now, to store this data, let's say I'm going to store this data in data node 1. So objective of this name node is basically a master, and these are called as the slave nodes. So this is called as a master node. This is called as a slave node. Objective of name node is to know where the data resides, or in which node, in which location the data resides. So let's say if I have a 500 MB file, name node will know that okay, the transaction data uh, it is stored in data node 1, and it is of the size 500 MB. So name node would be aware of this. Similarly, if there is another file that comes in and it resides in data node 2, name node will know okay that in data node 2 we have a, say, customer file. And so whenever there is a read happening, name node will know okay, if a application asks to read the data for transaction, he knows that okay, this data is available in data node 1. So this is how this is why we require a name node. It keeps all the metadata of SDFS. So it knows all about all the files that is stored in these locations, what all nodes we have. Like if we have 3 nodes, how many nodes are active. All those information is is present in the name node. So this is a high level like how data looks like. So as I mentioned, it stores all the metadata. Like we have a file this, and this is present in the data node 1, or this is present in data node 2 or data node 3. So one more thing that we have to know about is, let's say there is a concept of a rack. So let's say we are having a 10 nodes cluster. Okay, so we have said this is a node 1, this is a node 2, this is a node 3, and this all resides under one rack. So there is a rack which contains multiple data nodes. Similarly, we might be having three nodes in a different rack, DN4, DN5, DN6. Similarly, we have different racks like data node 7, 8, and 9. So let's say we have three racks where we all different data nodes are available. Name node knows about this, that okay, DN node resides in rack 1. Then the data node 2 also resides in rack 2, rack 1, and data node 8 resides in rack 3. So name node is aware about it, that where is the data node present. So it knows that okay, the in the rack 1 data node 1 is present, and in say the node 2, rack 2, we have the DN5 present. So whenever it stores the data, it is aware about where we have where we have the memory available. So it might be possible that we don't have enough space available to copy the data in a data node 1. So it will have all the information of where this data is stored, where we can store the data, or what all memory space is available, or disk space is available in a data node. So it keeps a map of all of these things, that okay, these data is the data is available in which node for which file. So with that in place, now main objective of SDFS was that we can process the data in parallel. And let's say we have a 500 MB of a file, and we store in data node 1. So this is a data node 1 which stores all the file in one place. So if we have such arrangements, then we won't be able to take the advantage of distributed processing. So we have multiple nodes available. We have data node 1, 2, 3, 4, 5, 6. Like that, we have, like say we have 9 nodes. If we are going to store the data in one node, and if I run a MapReduce job, it will be only able to read the data from one node, and all these nodes will be idle. Instead of doing that, what if there is a mechanism to split this data or into blocks and store different data in different data nodes? So from out of 500 MB, what if I can store 100 MB here, 100 MB in some other node, similar to that 100 MB in some other node, so that we have, like, if we store this data in four different locations, four different data nodes, then our MapReduce job will be able to read the data in parallel, and it can process the data in parallel, and thereby just we are able to complete the job in a lesser amount of time. So instead of storing all the data in one location, what SDFS does, it creates a block. So it creates block of 128 MB. Okay. So whenever the data is getting stored, it is not getting stored, like all the data is not stored in one place, but it will be stored in a block of 128 MB size, which means that if I have a transaction file of 128 MB, sorry, if we have the transaction file of size 500 MB, it will be stored in four blocks of 128 MB each. Okay. So what will happen? Now I have, instead of having one file, I have four files. Four files can be read in parallel and processed in parallel. the number 128 MB is with is Hadoop 2. In Hadoop 1, we used to have a file size of 64 MB. So each block will be of the size 64 MB in Hadoop 1. Since Hadoop 2 has been used pretty widely, with that 128 MB block size is something that we look for. Also, all these configurations are all these like what should be the block size. It is config driven. So there is a config file where we define that okay, the block size should be of 128 MB. Now someone can argue that what if my data is of say 576 MB, something like that. Okay, how it will store the data? So I know that I can store the data in 128 MB blocks. So I'll be having 4 blocks. So 128 MB here, 128. Similarly, we'll have here. So it is 256 now. Similarly, we will have here, and here if we are going to store the data. So overall 512 MB data we can store in 4 different blocks. Now we have some delta that we have to store, like we have around 60 MB, that 64 MB that we have to still store. So if I have to create another block of 128 MB, we would not be able to fill in the complete block. We would be able to only fill half of the block. Then what about this? How will what we will do of this block? This particular space will get waste? No. So HDFS takes care of that as well. HDFS will say, okay, I have 4 blocks of data where our data is stored for a file, and this contains 512 MB data, and the 64 MB data which we are going to store is in block 2, sorry, block 5. And out of 128 MB, we have consumed 64 MB, and we have 64 MB left. So if there's another file that comes in, let's say if there's another file that is going to come in of say 200 MB, it will start using the space that is left in block 5, and again it will have another blocks where it will be storing the rest of the data. So such type of logical splitting, logical blocks, these are called as splits. So we can store the data in parallel, sorry, in different blocks of 128 MB. And if the data is, if we have, incomplete blocks, then that blocks can be used for the other files. And the separation is called as a split. Now someone can ask, what is the size of data? Since we are saying that we should not have a 500 MB file, one file of 500 MB. And we can have the file of, we should have the file of 128 MB. What happens if we have file of less than 128 MB? Ideally, it is not recommended. Like it is recommended that you should have not, you should have a file of optimum size, like 128 MB is the optimum size of the block. And the best way is if we have 128 MB data blocks, then each block will be having 128 MB data. In the like I mentioned, there is a name node. Name node keeps the track of all the metadata. So if this file is present in 4 blocks, name node will know we have a transaction file, transaction say 12th December. This particular file is placed in 4 blocks or 5 blocks, and this is the location of this block. Now, let's say if we have very small files of say 1 MB or 2 MB in size, problem with this will be name node have to keep a track of all the files, all the data that is available. And if you have the data of 1 or 2 MB, name node have to keep the track of all the metadata. So if say I have a 100 GB files and we have to store it in a small size of 1 or 2 MB, amount of metadata that name node has to handle will be of the order of 100 GB. Like, for each data block, we have 1 MB file. So for 100 MB file, we'll be having 100 records in the name node. Like it will have to store the 100 locations for the this like metadata for the 100 files. If there are 1,000 small files, then it has to store the information of 1,000 files, like where this data is located in which block. So in such cases, if there are very small files, and this is something I'm talking about only one type of data, like one file, transaction file of 12 December. So if we have multiple files splitted into 1 or 2 MB in size, name node will go down because it won't be able to handle the metadata. It has to keep everything in memory because if I am going to perform any operation, I want to know what are the number of files and I want to read the files. Name node will not go into disk and look for the locations where this data is present, but it will be storing this data in memory to to leverage the high performance of a CPU of a RAM. If the data is stored in disk, then it will take more time to get the information of actually where my metadata, where my data file is present. So to know where my data file is present, we have to make sure that all the data is available in memory. So name node takes care of that. But if there are multiple small files in place, it will it won't be able to store all the information and it will go down. So this is something that we have to keep in mind about a name node. Now, this is something how data is organized in the name node. I have talked about the concept of rack. Now let's say I have a name node and I have rack 1. We have multiple nodes over here in rack 1. Similarly, we have multiple nodes in rack 2. And likewise, we have multiple nodes in rack 3. And now think that you are working on a production environment and you have a transaction data present in DN node 1. This information is stored in name node, like there is a transaction file. Part 1, like say block 1 is present in data node 1. So let's say this is some type of information that is stored in name node. Now, since these are commodity hardwares, these are not very much there is a possibility that this can go down, like data node 1 went down. Now, if I want to read this particular data, the data that is present in block 1, and since the node is down, and it might be possible that we are not able to recover this node, so we would be losing data. We would be losing, say, since we are storing in a block of 128 MB and only one block is present in data node 1, this 128 MB data will be lost. To avoid that, we have a concept of a replication. By default, there are 3 replications of the data that we have that we want to store is made. So this is rack 1, this is rack 2, and this is rack 3. Now, whenever we store the data, what name node does is it asks data node to do a replication factor of 3. So if let's say I uh, I have this particular data file of 128 MB in size. So at first, let's say we are going to store this name node told that okay, start storing data in the data node 7. So this particular file will go here of 128 MB in size. This will be the first copy of the data, and this will be in the rack 3. If this is in rack 3, then other copy of the data will go to say rack 2, and it is getting stored in the data node 4. So this is the replication. So we have 2, and the third copy of the data will be in the same rack but on a different node on the DN5. So this is how now say DN one of the node like DN7 fails, then we have 2 copy of data available in rack 2. Even if DN5 fails, DN4 fails, then we still have 1 copy of the data available in node 5. So there is a possibility that one particular rack goes down, If one particular rack completely goes down, still we have other rack that is able to, that is having the data that is stored in this particular node. So if rack 2 goes down, we know that we have the data, one copy of data available in rack 3. So to store the data, first we store the data in one data node in one rack. The other copy of data goes to another rack on a, say, node 2, and the third copy is in the same rack in another node. So let's say this is dn4 and this is dn5 and this is dn1. So first copy is in dn1, other copy is in in the rack 2 of and dn4, and the third copy is in the rack 2 and dn5. So data node, we have stored the data in three different data nodes, one in two in same rack and one in a different rack. So whenever a rack fails, still we have one copy of the data available. So this is possible with the help of a replication factor 3. Okay. Also, there is a concept of a rack awareness. So rack awareness meaning that, let me clear the screen. So there is something called as a rack awareness. Now, Namenode knows all the information about this rack. It knows that, okay, in rack 1 we have 4 nodes. So we have 4 nodes available here. We have say 3 nodes available here in rack 2. So Namenode knows that we have currently 2 racks and we have 6 data nodes available. Now, if one goes down, let's say dn1 went down, it knows that dn1 is down. Now I have 5 available nodes, 5 available data nodes. So this concept is called as a rack awareness. Okay. Now, how does Namenode come to know that this data node is down? These are connected system, but how does it knows that this particular node is down? So idea is, Namenode is expects that every 3 seconds there is a heartbeat that will be sent to it. So each data node sends a heartbeat. Heartbeat may be a like a simple call that if it is receiving the heartbeat from each of the node, in every 3 seconds, it knows that, okay, this node is healthy because I just received some communication from a data node 1, or we received the communication from data node 2. Okay. So with the help of a heartbeat, Namenode understands that the data node is alive, like there is no issue with any of the data node. If any of the data node does not send the heartbeat, Namenode will come to know that, okay, this node is now down and I only have 5 racks available. So this is how Namenode stores the information, and it knows about all the data nodes that is available, and it also knows about all the racks which contains those data nodes. So we have talked about this. There is a concept of secondary name node as well. Since name node is a single point of failure, we can't have only one name node. What if this particular node goes down? Everything, all the information where this data is present for all the files, it is in the name node. And if this name node goes down, data is still present, but we don't know where transaction data is stored. This information is uh, contained in the name node. And if name node goes down, everything goes down. So to avoid that, we have a concept of a secondary name node. So secondary name node will be having the copy of the name node, and this copy gets refreshed at a at a particular time interval. Let's say every 10 minutes, this name node, if there is any delta, new files came in, or new blocks created, all this information is sent to the secondary name node. So if a name node goes down, we have all the data stored in the secondary name node, and we will be there would be, of course, some downtime, but it won't be a very large downtime. But yeah, if first name node goes down, secondary name node will pick up, and it will take care of all this cluster. We have talked about fault tolerant, replication factor. We have talked about the heartbeat. Scalability, we can add as many name node as we want, or sorry, as many data node as we want. So today we have 10 data nodes. Due to increased demand, I now want 20 data nodes. So we can add, and also these are very cheap hardwares. So we call it as a commodity hardwares. So these data nodes are very cheap in nature. So it is a very uh, we are easily able to scale such data nodes. So whenever we need a new disk space, we can add more nodes and we can rebalance. As I mentioned, applications, all the applications are built on the top of SDFS. Like HBase is on the top of SDFS. Similarly, MapReduce is also built on the top of SDFS. I have talked about data split blocks, and we have the replica, like we have the copy of data available. We also talked about that first replica is placed on the say data node 1. Second replica is on the data node 2 on a different rack, and the third node is on the same rack. Like this is in rack 1, this is in rack 2, and third node is in the rack 2, but on a data node 3. So we have discussed that first node is where first rack stores only one copy, and rack 2 stores two copy. Now what if there is a SDFS read is going to happen? Now we have all the data stored in SDFS. Now I have a application. Let's say we have a MapReduce application, and it wants to read the data. Then how it will read? So there would be a SDFS client which will connect to the SDFS file system. It will get the information about all the blocks from the name node. That okay, I have a file, transaction file, like I mentioned. There is a 1 GB file, and this 1 GB file is stored in a block size of 128 MB each. So it will give me name node will give me the address of the blocks where these blocks are present. And once I have those information, this SDFS client will create an input stream, and it will go and read the data from different data nodes, and it will get the information of all the blocks and this data node. This is how SDFS reads the data from different data node. So we first go into we make a connection with SDFS. We ask for the file. Name node will give me the location of files, and then SDFS will using the data input stream, it will go to each data node and say and ask the data node to provide me the data for this file. So it will say that give me the location from the node 1. It will ask that give me the data for this particular block. So data node will uh, send us the data, and this is how data read is done. Now, if I want to write the information into SDFS, again we have to create a connection with SDFS. So SDFS client will do that. It will come to name node. Name node knows about racks. It knows about where we have space available, and it will give us the location of the blocks where we want to store the data. So first we create the connection. This will start writing the data into the data nodes. So if you see, the write function is called, and we start writing the data into the data node. Once the data start coming into the data node, it will perform the replications. Like from data node 1, we are going to replicate data into data node 2 or data node 3. Once that is done, we acknowledge that we have written the all the data that we want to write in SDFS. Once this is done, the connection is closed, and all the information of the blocks where the data is stored, it is now available in the SDFS or in the name node. So whenever a new application comes and asks for this particular data, Namenode knows, okay, this data is stored in 3 data nodes in different blocks. How security is maintained in SDFS or in Hadoop. So there is a concept of a Kerberos. Kerberos is used for granting the ticket. So there is a concept of ticket granting ticket. Whenever someone wants to log into SDFS, they will have a concept of a Kerberos, where we have something called a principal, and there's something called as a key tab. So principal is basically each user will have its own principal. Like say, if there's a user John, there would be an email for john.wick as @ let's say gmail.com. So this may be his principal meaning that this is his identity. And there is a key tab. Key tab is a file which actually provides us the access. When you log in with this principal, it will look for a file which is called as a key tab file. When you have these two information, you would be able to log into the SDFS nodes. Okay. Now file-based access, like in Linux, we have read, write, and execute access. Same pattern is followed in SDFS as well. So we have a owner, we have a group, and we have a node. Uh, sorry, owner and group and a mode. So if I want to make someone owner, like we want to give the RWX like 777 permission, we have to use the same commands like we use in our Linux file system. We can also implement ACLS. ACLS is access control list. We have one property where we can say that we want to enable ACLS. There are multiple commands. It will look similar to what we have in in our Linux file system. Like if you want to list a file from a directory, we say ls, and we say slash user slash data and something like that. This part similar to this, if we have to list the directories in SDFS, we use the command sdfs dfs -ls and the path to the directory. So if I want to know what all files are present in the transaction directory, we will say sdfs dfs -ls and the complete path to the transaction data. Similarly, if you want to create a directory, we can use mkdir. If you want to remove the directory, we can use rmdir. If we have a file in our local machine and we want to copy this file into the SDFS, we can use the copy from local. And if you want to export the data from SDFS, we can use the copy to local command. So SDFS DFS is the common in all, because this is how it knows that this is an SDFS command. If we want to remove, we can use -rm. If you want to view the content, we can do cat. If you want to move, -mv. And if I want to know how much space is how much space is consumed by different directories, we can use sdfs -du -h. So these are different commands that we have in SDFS. There are multiple commands, but these commands are used in very often. Like as a developer, you would be using these commands very often. So this is all about SDFS. Thank you.